Started. Hey everyone, welcome. I am Jared Longfox. I am one of the hosts of this AIAA Space Resources Technical Committee Space Resource Webinar Series. Um, Today we have Major Brandon Dotson with us from the United States Army in in the University of Central Florida. He's going to do an intro himself, so I'll save that. But as far as logistics go, we're going to be saving questions till the end. If you have them, there's a Q&A feature that should be on the bottom of your screen. Feel free to punch questions in there as you have them, or you can wait until the end for the Q&A session and we'll get to them. If there are any tech issues, like you suspect everyone's audio dropped out or anything, please punch it in there as well. I will be monitoring this. So without further ado, Brandon, please take it away.
Okay. Yeah, thanks, Jared, and thanks for having me. I think I've been a member of AIAA since like 2010, not to date myself. So it's a real privilege to meet with y'all today and kind of talk about some stuff that I have been working on. Going to talk about a whole host of different topics here and somehow hopefully stitch it together into a coherent topic, all related to landing on the moon. But before we jump into it, I do want to take a quick second to acknowledge the passing of a real founding father in the field of space exploration, Dr. Ed Stone, who passed away about 2 weeks ago now. Dr. Stone, among his many titles, was my graduate advisor at Caltech, and one of the early founding fathers of the field. He was the project scientist on Voyager, the only spacecraft to visit Neptune and Uranus, and the first ones to venture out into interstellar space. He was the head of the Jet Propulsion Lab out in Pasadena, California, from 1991 to 2001. So he oversaw things like us going back to Mars, the launch of Cassini and Galileo out of Jupiter. So really a tremendous loss for the community, and I'm definitely grateful for all the Friday afternoon chats with him where I'd go in and try to explain why my computer code wasn't working, which is, not embarrassing at all. But so with that, a little about myself. As Jared mentioned, I am a major in the United States Army. That all started because I did my undergrad at the U.S. Military Academy at West Point back in 2010, where I'd studied physics and chemistry. From there, I was fortunate enough to go straight to graduate school at Caltech, as I mentioned, where I did a master's in physics as a graduate research fellow. I had the unique opportunity to work for both Dr. Stone and at JPL, working on some space propulsion type stuff, really studying plasma physics in both cases. Went back to the Army, went off to flight school for a bit, a stint in Afghanistan. While in Afghanistan, did some more coursework with Georgia Tech to pick up a master's in aero, mostly focused on rocket combustion type stuff and helicopter design. Before going off to the U.S. Naval Test Pilot School, where I learned to test aircraft and fly different airplanes and helicopters and whatnot. Did that test pilot gig for a few years before coming down here to Orlando. Just about to finish my second year as a PhD student and now PhD candidate in physics with a focus on planetary science. So just to rattle off a little bit about who I am, but my main research focus here is on plume surface type stuff. So how do rocket plumes interact with both lunar and Martian simulants? What are some of those geotechnical properties? How do they affect? And I'll kind of step through some of these as we go today. And definitely like to give a shout out to my committee with Dr. Dan Britt, Philip Metzger, Addie Dove, and Tony Colapret, who's working on the Viper mission here, about to go to the moon soon. So with that, it's an exciting time, right? As we look at Artemis and it's starting to ramp up. Of course, the picture on the left here is Artemis 1 and its flyby around the moon. First human-rated spacecraft to do that in quite some time. And Artemis 2 here on the docket coming up September of 2025 to basically repeat that with humans on board. So a really big deal. Awesome time to be involved in all things related to space. But definitely one of the important things as we go through Artemis is, well, obviously we want to land and we want to build some stuff and take back off from the surface. And so a lot of what I'm going to be talking about today are a couple different topics related to that. And when we talk about landing on the moon, the classic case of why we should care, or kind of plume surface interactions in general, is with Apollo 12, where basically in this picture here, this first thing here in the foreground is actually a different robotic spacecraft called Surveyor 3, which landed on the moon several years before Apollo 12 went and landed in this module you see up here on the ridge, about 200 meters away. And in doing so, of course, they kicked up quite a bit of dust when they landed. Even given the size of the lunar module, they were up on top of a ridge back then. But the astronauts brought back pieces of that Surveyor spacecraft, and one of my advisors, Phil Metzger, was able to look at some of this equipment and see the actual damage to the structure where it was effectively sandblasted, right? We see pitting and cracking of that. And so really, as we go back to the moon, and this time with larger vehicles, we really want to understand what those effects are when we're trying to land in the same place over and over again, maybe build a base, and what these larger, heavier vehicles will mean when we land on the moon. So before we go and do any sort of landing, be it on Mars or the moon, right, we have to obviously do the modeling to understand the risk of what we're getting ourselves into. And that modeling is driven largely by physics, right? The equations, which it may not surprise you, even though we landed on the moon back in the 60s, that a lot of these equations are poorly understood. And I'll kind of talk through some of that later in the talk. And so those equations are driven by experimental work, some of which that I'll cover here, and some of the initial results. And really, when we talk about plume surface interactions, a key piece that I'm going to spend a bunch of time talking about is the surface part, and in this case, some geotechnical properties, which kind of tie this all together, right? There's modeling of the behavior of granular material. How does it influence those equations, and what do we learn from our experiments? So before we get into it, I'm going to kind of do a deep dive here on the geotechnical part and explain some of that in a little more detail, just to kind of give an overview of the surface part. So without further ado, though, as we talk about it, the main thing that kind of governs the lunar environment, right? If you just look at this picture, it's largely based on impacts, right? That there's no atmosphere on the moon, just constantly bombarded by debris and small bits, debris, and cosmic rays, all the sorts, including the South Pole Aitken Basin, where we're going to land, which is a huge impact area. And this picture on the bottom right, which is not the Death Star, that's actually a small grain with an impact on it. So you can see on all scales that that impacts dominate the lunar environment. I mentioned getting hit by cosmic rays and micrometeorite bombardment and solar wind. This causes some of the particles to break down, but it also causes things like nanophase iron to basically form in the material, which changes the behavior. And we see this from some of the old Apollo days, right? Like this rock, you can see where all the small bits have kind of broken off from those impacts, like over hundreds of thousands of years, right? I mean, the moon, we're talking like 4 billion years of just being blasted by all sizes and shapes of particles. And the astronauts reported this back in the day, right? It's stuck on everything, seals, their suit, caused them to have lunar hay fever is what they referred to it as, where it got into their respiratory system. And we see that really as we look at the surface, when I'm kind of throwing out the term regolith, we're talking about that top bit of all the kind of small fragments and granular material, and that continues down for some bit before you get to kind of larger chunks. And so with that, when we talk about geotechnical principles, I'm not a civil engineer, but just we'll kind of do a quick recap of what some of these terms are before I jump into the actual data that we've been doing in the lab here. So shear strength is an important one, right? It's related to the maximum amount of force that you can put to shear something before it fails. And this also influences things like bearing capacity and the ability to drive on stuff. And that's related to things like cohesion, or essentially like how sticky the material is inherently, and internal angle by this linear relationship here known as the Moore-Coulomb failure criteria, which I've sort of plotted here. So the x-axis in this case is normal load, or the amount of load that you're pushing down on, sigma s here being shear strength. And then basically that y-intercept is what cohesion is. Now, it's important to note that for low gravity, like on the moon, or with low normal loads, it's not quite linear in some cases, but for the purposes of this study, we're treating them as linear just to kind of make it easier in the math. but keep that in mind as we go forward. So, and as I kind of mentioned, right, these parameters drive things like landing pad design, the foot pads, how large they were right back in the 60s. We didn't know. We thought we were going to potentially just keep sinking down through that regolith layer. And certainly if you're doing anything like construction or building infrastructure, these are important things to think about. And as I'll talk about here and attempt to stitch together today, they are very important when it comes to plume surface interactions, right? So you have a shearing force, if you will, of flow going over a granular material. So things like cohesion, shear strength, and particle size do play an important role in that, as we'll see. So when we talk about cohesion specifically, or that y-intercept on the Moore Coulomb, as you remember, there's a whole bunch of things that go into that, right? Some of that is just the particle shapes and sizes. Moisture content here on Earth is obviously important. And some of those interparticle forces like mineralogy, the electrostatics. And as I'll talk through here, we'll see that density actually plays a very, very, very important role in that. So fortunately, being at University of Central Florida, we have access to a lot of high fidelity lunar regolith simulants. And what these are basically, we match the mineralogy of the samples that were returned from Apollo, as well as particle size distributions to really get a close working both from the minerals and from the mechanical behavior of the granular material. So we have things like lunar highland simulant and the mare, right? The mare is like the dark parts of the moon when you look up at it at night. And some of these older ones like JSE1 and Black Point 1, which were used historically to kind of mimic these. So we basically made our own little test device here where we do these shear measurements to kind of understand what those parameters look like experimentally. And how this works is essentially you have a box, you fill it with fake moon dirt, and you shear it, and then you read out the force as that happens, and we do that with different normal loads on that. In particular, we did this. Well, this is kind of what it looks like when you put a bunch of different normal loads on it. You get that same linear relation that we mentioned, and then you can calculate what the cohesion is. And this is just for one density here. And it's essentially, we repeated this for a number of different densities. And I'll kind of show you some of that data just so you can kind of get a feel for what I'm talking about. So that last graph that I showed with the line, that's essentially 1 point on this curve. So this is just for lunar highland simulant. And I'm going to build this curve just because it gets a little confusing with all the lines and stuff. So I'll kind of step through it. But essentially, if you vary or increase the density, what we found is that the actual cohesion or inherent stickiness of the material increases, and it increases exponentially. And it's not just for LHS. We saw this with all the other lunar highlands and mare. Some of these are the lunar dust ones where the particle sizes are much, much less. And that's kind of why you see this like, two different populations on here. And when we look at the moon and compare that to some of the historical data, we see, from the early Luna days from the Soviet Union, generally kind of fall within this ballpark. There's not a lot of great reporting coming out of that, so we kind of have a large area on here. Surveyor, I mentioned that spacecraft earlier. This is kind of the range that instrument observed on Surveyor 1 in particular back in 1966. And then all of the Apollo ones, if you look at this document called the Lunar Source Book, you'll see generally everything falls in this range. So we see from our experimental measurements in atmosphere that the numbers are actually kind of in the ballpark. I know this is supposed to be about the moon. I'll add on here some of the Martian ones just to show the similar behavior we get from those regolith simulants. One of the Mars missions back in 2022 published this range to see that, yep, we're still in the ballpark. We did some glass beads. You can't compact those as much, but generally falls in the same. And then some of the previously published data, we see that agrees with our results as well. So a lot of that to say cohesion, or the behavior of the material inherently and how sticky it is very much dependent on density and increases exponentially. So with that, I mentioned internal angle, which is essentially the slope of that Moore Coulomb relationship. And I'm just showing a whole bunch of points here to show both lunar, Martian, the glass beads, all of that, of kind of what that looks like when you look at that across density. Again, we compare that to previous data. We see it's generally in the ballpark, anywhere from like 30 degrees up to about 70, 60-ish. And what that means is you get to angles that can be a lot steeper before the material fails, which will be important later. And again, some of that Martian stuff looks like it matches pretty well. So generally we fit this with the line, it's a rough order cut here, but we do see from that internal angle does change based on sample density, which is another important piece. So what we did is we then took all that, we put it in a vacuum chamber, and we started to pump out the air, pump out the absorbed water, and repeat these measurements to see what effects that would have. And so there is a NASA standard out there that says you should bake material for a certain amount of time, above a certain temperature range. The reason for us doing these tests was really to kind of do a sensitivity analysis of, okay, if we were trying to do a large amount of regolith simulant, how long will we need to do it to really make it worth the cost and effort of preparing the sample before testing in vacuum. But generally, we're only pumping down to like 160, 170 millitorr, which is low enough to get the water vapor out, but not obviously like a hard vacuum like you'd find on the moon. And so before I showed all those charts in atmosphere, I'm just pulling out the LHS and the LHS-1D or dusty, the finer grain particles here to kind of show you what this looks like in atmosphere. And as we did our tests, we found some weird results, which was that when you do these in vacuum, they plot down here for LHS and down here for LHS-1D, which essentially means, the cohesion decreases under vacuum. And that may be a little weird, right? When you hear people talk about the moon, you probably have heard them mention, oh, the material on the moon is so much more cohesive. And what we find is like, that's not necessarily the case. And this next part will explain why. So again, the internal angle we mentioned before, what kind of angles you can get to before the material fails. This is the old data from before. Now, if I show you the ones in blue here are LHS in atmosphere, and the ones in green I'm highlighting are the fine grain ones in atmosphere. We do the same thing in vacuum. We see an increase for LHS-1 and a similar increase for LHS-1D, the fine grain dust, which is to say that internal angle increases significantly under vacuum conditions. So that is why you see things like these very well-defined boot prints or rover tracks, right? It's not necessarily because the material is more cohesive, it's because the internal angle is much higher once you suck out some of the water. And so to think about this, I showed you a series of exponential curves, but essentially this is a three-dimensional surface, right? In one case, you have density on one axis, the normal force, or how much I'm pushing down on another, and that surface will pretty much tell you kind of like what the shear strength is. So I'm showing here these black dots for the actual data that we recorded. And if you really squint hard enough, this kind of edge here along zero normal force, well, that is cohesion, right? That is the inherent stickiness, if you will. Well, so as we mentioned in vacuum, that cohesion decreases. And we mentioned that internal angle increases. Well, internal angle would be essentially the slope along this edge. And so what we find is when you put this stuff into vacuum, the whole surface kind of shifts, which is a long-winded way to say that basically the overall behavior of the granular material, the shear strength, its relation to density, how it behaves, changes when you remove the ambient pressure. So that's a huge finding. So what's going on here? We have some thoughts, but when I go back to this list of all the things that contribute to cohesion, there are several here that I've now highlighted in blue that would essentially be affected if you take out the water, you take out the air. And so I think there's kind of this delicate balance of which one dominates. And once you remove the ability of water to do some of these interparticle forces, other things like electrostatics might dominate, or that particle interlocking might dominate. So been talking a lot about, let's see how I'm doing on time. Okay. Hopefully I haven't put anybody to sleep with the geotechnical stuff, but just to kind of recap that one particular piece about geotech, we see that material behaves very different in vacuum, and that density plays a very large important part in the behavior of these granular materials. And so this is important when you think about testing instrumentation on Earth. If you're using these simulants, if you plan to build stuff with them, or test instrumentation, or drive on them, or test your rover wheels, these are things you kind of need to think about, right? That the behavior changes, and it will likely change when you get to the moon. So long-winded way to talk about that first part. Now I'm going to kind of spend some time talking about how does this relate to some of the Plume stuff. And before I do that, I'll kind of give a little bit of background on plume surface research and at least where we are so far on it. So plume surface interactions, really talking about the erosion of granular material when you land a rocket on it. And there's a couple different mechanisms that drive that have been highlighted over the years of research and tons of people looking at this. There's things like viscous erosion, which is essentially that straight shearing a bit. And that's largely significant as this paper highlighted back in 2020 for landing on the moon. This is what we saw during the Apollo days of things literally being blown or scoured across the surface. There's bearing capacity failure, which essentially is like it sounds, exceeding the bearing capacity or the ability of the surface to handle the downward force or pressure on it. Diffuse gas eruption and diffusion-driven flow, where essentially you have within, in this case, this is the crater being produced from an exhaust jet. You get motion of the granular material. And that's because the granular material kind of behaves like a fluid in some cases, and it kind of behaves like a solid in some cases. And so, but for the purposes of this, we're largely focused on this blue bit, which is viscous erosion and scouring, since that will be the most dominant on the lunar surface. So here's one of the experimental setups that we're using here at the Florida Space Institute. Essentially how this works is we have a box here that we fill with that same fake moon dirt, if you will, the regolith simulant, and we have a hose with some high pressure gas that we shoot in, and we use a GoPro to kind of look through this clear plate to look at the crater formation over time and to try to really understand those fundamental equations governing viscous erosion. In this case, as I mentioned, density is a very important bit and changes the behavior. So we control the density carefully and we measure the density carefully using gamma ray attenuation. Essentially, we shoot gamma rays from cesium-137. This is kind of what the energy spectrum looks like from cesium. You get this nice peak. And essentially, you measure the height of this peak as it goes through the sample, and then you can calibrate that to what the actual bulk density of the material is. And we've recently started trying to take measurements in layers so we can kind of understand how the density changes with layers. And we use a vibe motor to basically compact it so that way we get an even distribution of compaction. Again, I mentioned, we have Lunar Highland simulant, Mare, some of the dusty ones. That's really all I'm going to be reporting here. We've done tests on all the other ones and some Martian simulants as well, but we look at different exhaust pressures and densities and flow rates and stuff. And so what this looks like in execution is, it's kind of hard to see as the dust starts to kick up, but essentially we track what this crater is doing over time. And that tells us a lot about the fundamental physics going on between the interaction here. And so we go in and we use software to basically pick out the edge detection here. And we plot that over time. In this case, I'm just showing depth, right? And this looks like a very nice, like linear or logarithmic fit. So we put a fit to it, and we use that to fit different fit parameters. And I'll explain here as we go forward how those fit parameters are important for our analysis. So in that case, we look at A and B. So B in this case is a time-dependent one, and A is kind of related to some like fundamental time scale. Well, there's some work from one of my advisor, Dr. Phil Metzger, where he talked about basically the volumetric erosion rate is proportional to some of these fit parameters and cotangent of phi, where phi in this case is that internal angle that we mentioned before. It's really supposed to be the slope of the angle here, but in this initial bit, we've just plotted it based on internal angle to kind of understand the relationship of geotech to this. With that, he also has put out some papers where he basically showed that that same volumetric erosion is related to essentially what is the kinetic energy divided by potential in some cohesive term. And so he was able to derive this equation where C is some unknown constant. Well, here, I'll build it out so you can actually see. V is the exhaust velocity, A is the exhaust area, and then down in the bottom are kind of your surface or granular material parameters like porosity, packing ratio, the density, gravity, particle size. Bravo is like some lifting coefficient, which is just like a angle, and then alpha. So as we look at this equation, he was able to do some experiments in the vomit comet here, looking at different gravities to try to probe these relationships. So we're pretty confident that these ones are correct, like G and D are correct, and this obviously the top part is correct. But we don't know what C is, even after all the research, and we don't know what alpha is. And so in this case, we're going to look at some of the experimental data that I've produced here to kind of see if we can figure out what some of these variables are. Again, this is a busy one, so I'll kind of build it. So we look specifically at cohesion, using the cohesion that we determined in the first part, and the erosion rates here based on those fits that we had. Here I'm just showing LMS, so cohesion on this axis and then volumetric erosion on this side. If I build it out, LHS kind of falls somewhere in here, and that sort of makes sense. The particle sizes are about the same. And then when I use the thick marker, I can put a line through that that kind of looks like that. 1D, you kind of get a little different distribution. It's very similar, but shifted up and to the right. And 1D are smaller grain particles. And so what we see is that, yeah, okay, so it is about a relationship like the equations show. That alpha term does seem like it is somewhat related to cohesion. And there is likely some sort of particle size distribution dependence here. So how well does this equation fit when we look at those two relations together? So in this case, I'm plotting one equation on the x-axis and the other equation on the y-axis. And so if they're equal, they should generally fall on this green line, right? This is a line with a slope of 1. And so as I start to layer on the data, we see LMS, yeah, it seems to fit decently well. LHS, okay, seems well for some of the lower numbers, but then it starts to deviate, and similarly for the dusty material. And so all that to say that seems like a relatively good fit up to a point, right? All models are wrong, some are useful. And so we see that all, these models are actually kind of correct in one area, but we don't completely understand what's going on across the full spectrum of possibilities. And this is a shameless plug for Phil's work. He's got a couple papers here where he walks through essentially how he's derived these equations and then compares them to video analysis of some of the Apollo stuff as well. So definitely worth checking these out. They're in press now, but I think you can find them on archive for free. So from that work, what we see is that, yeah, this initial equation does seem like it's a pretty good approximation for the most part in these experiments. And then if I look at this equation, that term alpha that I mentioned, it does seem like it's somewhat related to cohesion. Phil's paper, if you read it, it mentions that it's cohesive energy density. So, we're kind of on the right track there, but we have to do some more research to kind of understand what's going on here with all of these variables. And we don't really understand like why it breaks down. And it might be because there's some sort of transition between regions, or maybe it's a turbulence in the flow. And so a lot more research to go here. Again, this is probably like the best that we understand some of these governing equations, and obviously they're super important for modeling. So with that, now let's talk about actually landing on the moon. I'm going to skip over the modeling part because that would probably put a bunch of people to sleep. But when we talk about this, how do you actually land on the moon? I figured it would be a missed opportunity as a test pilot in the Army and a helicopter pilot in the Army not to talk about some of the considerations for a landing vehicle itself, a human-rated landing vehicle. And then I'll talk about some of the stuff specifically with Starship, SpaceX's Starship, a little bit later on of what we've learned from previous launches. So with that, let's talk about human landing system in particular, and some things to think about as we go back to the moon. And this isn't like research that I'm actively doing now, but just some stuff that I've been exposed to and can kind of just give my personal opinion on it, I guess. But when we look at HLS as it stands now, right, like SpaceX's Starship is supposed to be used for Artemis 3, at least for now. And this thing is massive compared to what the Apollo lunar module was, right? Like it's more than 5 times taller. It's just massive, right? And even the Blue Origin entry, I think this design has changed a bit, but even that is still significantly larger than what was used in the past. And that's not a bad thing, right? Like it's good that we're able to put additional tonnage on the surface. But if you picture a human being sitting at the top of this thing, like significantly far away from the center of mass, that's a weird thing when you're trying to control a vehicle and you're putting inputs in and it's causing the entire cockpit area to move. And the proprioceptive feel that you get from that, even in 1.6G, is definitely probably going to be weird for those first Artemis 3 astronauts, particularly as you go into a dark and dusty environment like the South Pole of the moon. Speaking of the moon, right, of course, it only has 1/6 the gravity of Earth. And that actually does have some impact on control of the vehicle, right? So in your freshman physics class, if you were to draw the force vectors here, right? Like if I'm in a perfect hover on Earth, I have a certain length of force for that. But on the moon, because of 1/6, it's a lot smaller, right? So if I'm trying to affect this vehicle and get it to move either laterally downrange or what have you, I have to take the vehicle to much larger attitudes than I would normally on Earth. And it's because I have such a tiny little change in that vector. And so, unlike a helicopter on Earth, where, 30 degrees may seem like a lot of attitude change, on the moon, you could see significantly more than that. And obviously, you can't really go much past like 90. So, there are certain things that you can and cannot do with a lander on the moon. You might be thinking, okay, yeah, that's cool. We've been to the moon before. Like, what about autopilot, right? And yes, we've been to the moon, right, for all these Apollo landings, which were all kind of generally in the equatorial region. And not a single one of these actually touched down with fully coupled autopilot. Obviously, the famous case, Apollo 11, Neil Armstrong getting low on fuel coming in and taking manual control to steer it. But essentially, all of the Apollo landings were essentially what they called, I think, semi-autonomous. So where they let the computer fly basically the rate of descent profile, and then the astronauts themselves on the sticks to guide in for the terminal phase of landing, the actual lateral control and where to put it down. So there's guidance, right? It's helping you there, but there were people on the sticks as the vehicle touched down. And that's similar to what we see in helicopters now. We do have autopilots that will land to the deck, but there's definitely some drift in some of those things, and you have to watch them carefully and monitor those. So some things to talk about. How are they actually controlling this, right? Like, so this is the inside of the lunar module that was used back during the Apollo days, and they essentially had two inputs here. The one on the left is your thrust control, which I should hopefully not have to interact with if you're allowing the computer to fly it, and the stick on the right, which does a lot of your basically attitudes and rates. And so without getting too in the weeds here, I'm going to kind of give just a quick overview of control response and what that means from like an aircraft or vehicle control perspective. Just to kind of give you a feel for what we have now that we didn't have back then, that I think would actually be very helpful, given my experience of landing in dusty environments at night. And so when you look at control response, what I'm going to talk through a couple of these, but essentially I've shown a plot here that's overlaid. They're all on the same time axis here. The top part is stick displacement. So in this case, it's a step input. It's always going to be a step input as I go through this. This one here is rate, which is measured obviously in degrees per second. The actual attitude, which is degrees, right? How the vehicle is pitching or rolling, and then the velocity in feet per second. And so the most basic you can get is what's called a rate command attitude hold. And this is like what helicopters, just when they're purely raw with no flight control input added on, how they behave. So I put in a stick input and I essentially see this first order response, this nice kind of almost logarithmic looking response in rate. If I put the stick back to where it is, the rate goes away and my attitude goes to a set bit. So that's what RCAH is. That's what Apollo landed with. That's what helicopters use in their purest form. We talk about attitude command, attitude hold. I put in that same stick input. Now, essentially, I'm directing the attitude to do that first order differential. And the rate will do whatever it needs to do to accommodate that, right? And then the velocity, you'll have some sort of weird velocity that's going on. But this is particularly helpful if you're trying to pitch or trim to a certain axis. The next step, right, if I keep moving down here is linear acceleration command and velocity hold. So I put in a stick input. Again, the rate's doing what it needs to do. Attitude is kind of doing what it needs to do, and that's to achieve a particular velocity. And so this is helpful. Like if you're landing on the back of a ship, right, you would want to use something like this to try to match the speed of the ship so you touch down. And probably the most important for landing on the moon, and I don't want to spend too much time boring everybody with control response, is this thing called translational rate command, or TRC, and position hold. And so in that case, I put in a stick input. The rate does what it needs to do, the attitude does what it needs to do, and that gives me that first order response and velocity. And this is very helpful when landing in if I'm trying to hover over a particular spot, or I need to move the vehicle left or right, just like a couple feet, or if I can't see outside and I'm kicking up a bunch of dust. So while autopilot, might not be able to fly as completely in a human-rated spacecraft to the surface, even if it can, it's still helpful to have controls in case astronauts need to come into the loop and fix things. And some of these advanced control modes will help in that case, right? It would be a real shame if we spent all this money and time and energy and got, within 10 feet of the lunar surface and then had to abort because the autopilot wasn't doing it right. And so having some of these features would be helpful. And so how do you train that, right? So I mentioned back in the day, uh, Apollo landed and it was rate command attitude hold. And that's essentially what these basic helicopters were. So a lot of the Apollo astronauts learned to fly helicopters before moving into this thing called the Lunar Landing Training Vehicle, or the Flying Bedstead. And you can see why it got its name. This is essentially like a jet engine that's can either be fixed straight down or can be gimbaled, where they would basically simulate that 1.6G. So you'd get to those same weird attitudes, and you'd get that same control response that you'd expect in the lunar environment, which is slightly delayed. And so there were 5 of these built, and 3 of them were crashed. This picture is Neil Armstrong famously ejecting out of one down at Ellington. So today, we have simulators where we train this thing. This you can train some of it, but that proprioceptive and getting the weird attitudes, there may be a potential to use some of these eVTOL aircraft these days, right? Your things that are competing to be air taxis. There's probably a way to do that where you don't have to use a jet engine and be, beholden to having to eject out of them. But something to consider. And more importantly, crew coordination, and that's how the crew is working together in a cockpit to achieve a mission. I will say, having had the luxury of and the honor of going down to Johnson Space Center and getting a chance to fly on some of the human landing system simulators as they're kind of working through the development there with several other test pilots. It is very, very workload heavy for one individual, particularly if you're trying to also fly the rate of descent. It's pretty much impossible to do the attitude and rate bit and also the rate of descent. And so if you're landing into an area and you're not sure, we can use cameras and FLIR to kind of look at that area, but it's definitely a 2-person gig to do that. And so crews need to practice that in a similar environment to understand what calls are really crucial and how do we do it. And so with that, I'm going to quickly blow through some launch and landing pad considerations since I'm getting short on time here. And I'm largely going to talk about some stuff that we learned from the first Starship orbital test flight. I know I'm kind of all over the map here, but want to hit a couple different areas with regard to landing. And so for those who don't remember, back on 4/20 last year, the first Starship launched at Boca Chica, Texas. Back then, SpaceX didn't use like a launch system where they basically used like flame diverter or any of that. They just had a concrete pad with some high temperature concrete on it. And so this vehicle is large, right? Like it's much larger than the Saturn V, a significant amount of thrust and a significant amount of payload to orbit. So not something we see that often. And when you look at how they built that, again, I'm not a civil engineer, but how would you do that? How would you build something that would support that kind of weight? Well, first you dig a hole in the ground. You put in some concrete pylons, you fill it with some gravel, put in some reinforced concrete, layer it with your high temperature fondag, put in your launch mounts, and then cover the rest of the area with concrete. And we know that's what SpaceX did because when you look at all the aerial photography from back then, like this giant hole in the sand down in Boca Chica, right, is where they eventually built it. You can see here where they put in those pylons. You can still see the sand in here with concrete. They then filled it with gravel and put in the reinforced barring to make concrete, put in the launch mounts, and then you end up with a launch pad. But famously, right, that launch went off. It did get up to 38 kilometers, which is pretty cool in altitude. But eventually was terminated with the flight termination system and a huge explosion. But with that, the launch pad, and I've shown this picture before, was totally destroyed, right? It kicked up large chunks of concrete and this dust cloud. Just a huge explosion, right? So yeah, it's a little different than landing on the moon, but when you get a vehicle this size launching on Earth, we can learn a bit from that. And so chunks of that material, the dust material, fell down about 6.5 miles away. And at the time, a lot of folks online, including the Texas Fish and Wildlife Service, were reporting that this was pulverized concrete. Well, we had folks through the power of Twitter or X send those samples to UCF, and I'm going to quickly run through what we learned from analyzing those samples. So this is what they looked like in the top here, just very fine grain, what essentially kind of would look like dirt. But they also brought in and sent in chunks of that high temperature Fondag concrete, the regular concrete, some of the limestone that's in the area, and then we were able to get some of the beach sand off of that as well from that area. And so just to kind of give you a sense of where some of these samples were from, right? I'm talking like over 6.5 miles away, northwest of the launch site. And so as we went through them, we looked at those particles, we looked at the densities, the sizes, the shapes using some instrumentation here at UCF. We also looked at the spectra, right? So the unique signature that you get both in the mid-IR as well as Raman spectroscopy that we did through some folks out at Rice. And we were able to find that this material was not pulverized concrete. It was actually beach sand. Beach sand that likely originated from underneath the launch pad. And so very quickly, I'll kind of talk through this failure mechanism and how did this all happen and how did we come to that agreement or understanding. And so what you see, if you actually look at the launch pad, is about T plus 6 seconds. There's this large explosion, chunks go flying, and then this cloud starts to grow. So initially it's like all these are kind of equal, right? And that is largely based on where those mounts are. But then this cloud here grows and it grows very quickly vertically and around the rocket. I think some folks have probably seen this where you see these splashes out here in the ocean very far away, but these are like, several story building tall splashes. And so from the video, and well, yeah, this one of somebody's poor van getting hit by some of the chunks of concrete. But from the video, we went through and we were able to determine some of the angles and velocities from those particles. And they are quite high. It's higher than 45. So it's not just like a shearing straight out plume. This is like more vertical. And they're at speeds between 90 and 350 meters per second. And so when we look at the actual launch pad, and Phil Metzger, I'll credit him with coming up with this idea, is essentially the water table at Boca Chica, because they're so close to the ocean, is quite high. And we see this in their construction videos, right? There's water pooling even as they're building the launch pad. And so when you put a rocket on top of that, it heats that area up and essentially instantly vaporizes that, which will cause an increase in pressure. And that pressure has got to go somewhere and eventually will explode. And Phil was able to find this paper from, I think, 1992, which was from volcanoes, pyroclastic volcanoes, that talked about basically what happens when you have a cap rock with a certain amount of pressure. And basically you get a very violent explosion and you can predict the velocity and trajectory of the particles. And so that actually kind of matched what we saw here with Starship. And actually, that's not a picture from Starship. That's a picture from Starship. The top one is a pyroclastic volcano from Alaska. But that's the point, right? It's a very similar mechanism here that we see. And so in that same paper, they give some estimations here of what some of those might look like with a certain percentage of water and what the gas pressure might look like. And so just a rough estimate calculation when you look at the exhaust from a Starship and look at, a range of percent weight for water, we see that the ejective velocity actually matches pretty close to the 90 to 350 meters per second that we saw in the video. So that is to say, like, it doesn't take a lot of absorbed water to get a very violent explosion when you have a cap rock over it. And so potentially, that same explosion mechanism may have resulted in some of these engines going out. That's a bit speculation if Starship shot itself down. But and again, I would point out, like, I don't work for SpaceX. This was all independent researchers and just private citizens who sent these samples in for the sake of science. And so from that, we think we might have a new failure mode here for folks online who might be considering building landing and launch pads on the moon. Yes, thrust might not be the same, but certainly that mode is applicable to the moon. And we don't actually know what the water content on the moon is, but from that same paper, you see it doesn't take much. Even 1% is enough to get you, a pretty violent explosion. And so this does have some impacts on how people are designing vehicles, right? Like SpaceX is potentially looking at moving their thrusters farther away to try to limit some of the exposure to the lunar surface. And as I mentioned, it doesn't take much to cause that same sort of man-made pyroclastic volcano. Since then, obviously, SpaceX has made some updates, including this huge water deluge system, and it seems to be working, right? They've launched a total of 4 times now, and seems like the launch pad's surviving. But so now that I'm getting long-winded here, let me just return and I'll kind of step through everything I talked about, which is a lot. I'm sorry, I've been kind of bouncing all over the place, but first off, we talked about geotechnical properties, right? The granular material is weird. It's especially weird when you deal with it in vacuum in the conditions on the moon. And density is an important part, right? So if you're trying to land something on the moon, it would certainly help to probably compact it, but um, those are important things to consider, and especially when we practice here on Earth. In terms of the Plume experiments, right, we see that these equations are still kind of poorly understood, and we need to do a lot more of these Plume experiments, and hopefully in reduced gravity and reduced temperature, and reduced gravity with vacuum to try to understand how these change and how they scale with larger vehicles. And then, as I mentioned, there's some unique challenges from a human perspective of controlling a vehicle that's landing on the moon that should be considered. And then if you're building launch pads on the moon, it's important to consider some of these failure modes, like that buildup of pressure. So I know there are some folks working on breathable launch pads, that is a thing, but something to consider. So long-winded rant. I think I went over a little bit there, but with that, I'd be happy to take your questions. Thank you.
Cool stuff, Brandon. Um, so let's see. If anyone has any questions, please, yes, punch them in the Q&A. And then I'll wait a second because people take a minute to type. Otherwise, I will jump in.
Hopefully I put everybody to sleep so that way no tough questions here. Yeah.
Yeah. Okay. Well, darn it, Hannah. Hannah Sargent asks, great, or well, says, great talk. How do you think the grain shape may change the cohesion properties?
Yeah, hey Hannah, good to hear from you. Sorry I missed you when I was over in the UK, but yeah, so that's a great question. Turns out particle sizes are definitely important in the behavior. I would direct you to again, a shameless plug, a paper that we published in Icarus. Believe it was last year. It's probably dated 2024 though, where we looked at that relationship in particular. Initially, when we set out, we found there was an interesting correlation between basically if you had a more diverse particle size distribution, so a wide range of large and small particles, you get a lot more cohesion, right? And that sort of makes sense where just from a packing standpoint, right? Like if I have all similar size like glass beads, they can only get so close. But if I have a wide range of particles, they can fill in all the voids and cracks and become even more cohesive. So yeah, the particle size distribution is just as important as density in controlling cohesion and the behavior of granular materials like regolith.
Well said. Holly Engel asks, can you share those papers you recommended to the group? I will say file sharing may be a bit weird, Brandon. Either you can share your contact information or I can share mine. And if you send me the papers, I can send it however you'd like that to happen.
Sure.
And
Yeah.
Holly, I think I have yours from registration. So, I can get that out to you folks. So, Brandon, however you want to go about that,
Yeah, I
let me
can
know.
shoot it with you, Jared, and if that's easier. If you want to play middleman.
Sure, no problem. Holly, look for those soon. And thank you. So, Juan Carlos Arano Romero says, very complete presentation. Thanks. What are the expected thermal and mechanical loads on future lunar launch pads?
Yeah, that's a tough one, right? It kind of depends on what solution for human landing system you're talking about, and what the thrusters are. I think Phil Metzger recently did a paper where some of the velocities that you see coming out of a like an HLS size rocket would be on the order of like 300 kilometers per second or so. Temperature wise, it's hard to say because a lot of these are potentially like mono propellant catalyst type thrusters that may not necessarily produce like a ton of heat. But I don't know that I have like a great range of temperatures and pressures for you. But I know that paper in particular, Phil was showing that essentially if you were to land a rocket without a launch pad, that those velocities and the shearing force is so high that you could essentially kick up uh, regolith into lunar orbit, right? Because the escape velocity on the moon is not that high. And so that stuff would hang out there for other spacecraft to fly through for a very long time. So while I don't have like an exact range for you, it's certainly a lot more than we saw during Apollo, and something we should be thinking about, and smart people are definitely thinking about. And this is probably a appropriate time to mention, like I talked about a lot of these challenges here. I will like to highlight like none of these are unsolvable, right? Like I don't want to sound pessimistic. It is hard to land on the moon, but like I'm confident that smart people at NASA and different companies here helping with Artemis like will figure them out, right? Like this is our moment to shine, if you will. Sorry, long-winded answer, but back to you, Jared.
Of course, and again, well said. I don't see another one in the chat, so I'm going to jump in. How do you think, and I understand this is a complete, you have no way of knowing this for sure, but what do you think the angle of internal friction and cohesion are going to do in the presence of an icy regolith in
Um,
vacuum?
Yeah, that's a good question. And super tricky to repeat experimentally, right? Because especially with water and trying to freeze it and getting that bit just right, it would make sense. And again, I'm just speculating here that you would get higher cohesion and higher internal angle with ice, right? Like if you think about the voids between particles, and if I was to essentially fill those all in with ice, that should, in my mind, increase cohesion, just the inherent stickiness of it, and then you should be able to take it to much higher angles before it would fail, um, if it's all essentially frozen together. But total speculation. Yeah.
Cool. Yeah, no, I seems reasonable. Jim Head from Brown University asks, for HLS SpaceX landing, will landing dig a crater that may make it impossible for a lander to remain vertical?
Yeah, especially when you consider Starship. I mean, I've got the image here staring me in the face, right? Like this thing it's like 50 meters tall. And so you think about what happens if these landing legs are just like a little bit uneven and what that means for an astronaut sitting at the top. Now I can't really speak to what SpaceX is doing with regard to like leveling of the vehicle. I'm sure there are certain engineering things you could do to balance that. But to do it dynamically is certainly tricky, like in an environment where you're kicking up all this dust and trying to get it just right. So that's a challenging problem for sure, especially with a vehicle that long. Yeah.
Cool. Thank you, Brandon, and thanks for the question, Jim. Michael Lucas asks, or well says, nice to hear a pilot's perspective regarding landing a vehicle on the moon. Can you touch a little further about your comment about the pilot being that far above the center of gravity? Also, do you know if Lunar Starship is currently developing a simulator?
Yeah, hey Mike, good to hear from you. Yeah, so some the primary aircraft that I fly for the Army is the Apache, and the Apache has a whole bunch of sensors on it that you use to fly in the dark. And the sensors are on the nose of the aircraft, and you sit, obviously back towards the center of gravity, and you do end up with this weird sort of parallax bit where you're seeing it from one spot, but you're actually feeling it from a different spot, and that can do a whole host of things when you lose your visual horizon. And I mean, if you're sitting inside a cockpit like that going to the moon. But more importantly, if you think about sitting in the back of a commercial airplane, uh, you feel that yawing motion a lot because you're sitting far from the center of gravity, right? And so that sort of pendulum motion, if you will. So I would think if you're sitting on top of an HLS Starship, and this thing is going to these large attitudes to maneuver, you're gonna feel that, right? And your inner ear is more importantly going to feel that, and it may prompt you to want to do certain things to the controls that may otherwise not be natural. So yeah, interesting bit. I will say for HLS, what I do know is the government does have like generic simulator models that they're using largely to. So I barely touched on some of the pilot stuff in here about control response, but there are things like what do the inceptors need to look like? What are the force versus displacements need to look like? What are the breakouts, right? How far do I have to move the stick before I get an input to actuate? And a lot of those things, plus the symbology, what is the crew seeing? How do they interact with the interfaces? Like all of that needs to be worked out and is in the process of being worked out. But that generic model is the only one that I'm aware of, just from my personal experience that NASA is using to help solve those issues and design it, right? That's part of the reason why I think a lot of astronauts, at least back in the day, were test pilots, because a lot of that work is very similar to like what we do on aircraft. And that's not to say that like SpaceX or Blue Origin aren't also working through those problems, but the government has to understand the problem set well enough to write the requirements for those vendors to build to, right? So all of it's good. The government models and hopefully and more likely than not, the commercial companies are doing it as well to actually polish the design before we go. So
Cool. Thanks, Brandon. Good question, Mike. Last one. Jim Head again. How high is the center of gravity for Starship? Do you happen to know?
I don't actually. I mean, I know at least in its current design, right? Like the crew compartment and basically whatever payload would be up here in the top, and then you've got a couple of which should be essentially empty tanks, right? But down at the bottom, you'll be carrying a number of very heavy engines. So I'm assuming it'll be somewhere a little bit lower down, right? Than up here. But who's to say? And there are things you can do to obviously play with center of gravity. But I don't actually know where that would land.
Fair enough. Well, if you find out, let us know. Um, Anyhow, we are out of time. I will call it here. So, Brandon, thank you for an amazing and informative talk. Really unique, really useful, cool perspectives and cool work. Everybody who's on, thank you for attending. Stay tuned for next month's webinar. Be on the lookout for an announcement and have a great rest of your day, week, and month. Talk to you later, everybody. Bye.
Thanks. Bye.